Up next is Benjamin, and he will be discussing Suricata in German critical infrastructures. Benjamin, it's all yours.
Thank you. Okay, great. I'm very delighted to be here. Give you a talk about German critical infrastructures, the use of Suricata. We developed recently a product using Suricata for intrusion detection in German critical infrastructures. Who am I? I'm a security consultant at Ausekos GmbH. Ausekos is a security consulting company at Augsburg city, sited 50 kilometers in the west of Munich. We're 5 years old and recently 25 consultants, security analyst engineers, mainly focused on SCADA security, ICS security, and therefore mainly in the field of critical infrastructures. I was a researcher for ICS security a long time ago, and now on I'm consulting our customers in mainly technical themes, but I also consult some boring topics like ISO 20001 and this. Okay. I will talk to you about the critical infrastructure, who are critical infrastructures in Germany and what are their needs for intrusion detection. And then I will talk about the solution we provide and the solution how we use Suricata to provide intrusion detection for this SCADA and ICS networks. I will show you an example on one of the automation protocols called IEC 104, give a little conclusion on what have we done, what will be future work, how will we use Suricata furthermore. So, information security at critical infrastructures. In Germany, there's a critical infrastructure law. They are obliged to measures, state-of-the-art measures and security measures, and there's some branches like energy branch, energy supply, energy generation. There's the water distribution branch. There's IT and telecommunications. There's the food industry. There's public transport and so on, and they all use SCADA systems and ICS technologies to control their critical infrastructure, to control and operate it, and therefore there's a large need for security in these networks because there are somehow many security flaws. They must implement security management, they must implement state-of-the-art measures, and they have to report security incidents to the German Federal Bureau for Information Security, which then takes these reports and reports it to European Bureau NIS to give a nationwide and European-wide overview of security situation. And if you look at the picture, when does the critical infrastructures have to report security incidents? So they have to report if they detect APT attacks. They have to report if they detect attacks and attackers using previously undiscovered vulnerabilities in software and hardware. They have to report if they detect previously unknown malware. So all the business critical incidents have to be reported, and if you look at these incidents, they are really hard to discover. An APT attack is really hard to discover, and they don't have to report antivirus blocked events, they don't have to report hardware defects and so on. And if you look at the state of information security at these critical infrastructures, and if you look how the operators work, you will see they could only, at the recent point, they could only detect attacks which are detected by the standard antivirus software, by standard firewall appliances, and so on. Because there's a huge gap between the office IT security and the OT security. So everywhere where we look at the office IT, at our customers, they're really good. They're at a good state. But if you look at the ICS networks and the SCADA systems, they have real bad security. You can think about the security standard 10 to 15 years ago, which is implemented. So the detection mechanisms, they have no detection mechanisms. And they have another security flaws. So the OT devices like RTUs, like PLCs, like the SCADA systems itself are really purely secure. They get no updates. They have on some of the systems no antivirus scanning. They have really old firewalls in place. And if you look at network segmentation, it's commonly not used. So this is the security side, but on the other side, the operators are prone to interconnect their systems with offices, with maintainers, with internet connections, and therefore the attack surface gets larger and larger. And they have to do something, and that's one of the reasons IT security law said, okay, energy suppliers, water distributors, you have to implement standard state-of-the-art security measures, and you have to report. And if you have to report security incidents, you have to detect them. And we showed up at our customers' networks and talked with them about detection. And the main detection was luck. They only said security incidents from APTs I can detect if I have a lot of luck. And that was our point where we said, okay, there has to be intrusion detection on network level as one of the first measures to be implemented. And we looked out at the market, and we don't have found any intrusion detection system which fits our needs. And therefore, we got a really good contact to one of the SuriCata developers, and we said, okay, let's implement a system by our own. Let's implement an intrusion detection system tailored to the needs of critical infrastructures. So there are some incidents happened in the last couple of years. So there was the Havocs campaign and the Black Energy campaign. I think someone has heard about it. It was attack campaigns against critical infrastructures. Until 2015, these attack campaigns was mainly focused on information gathering, on gathering information about how ICS networks are defined. They have stolen information about the design of the networks, the design of the systems. And there was a break at the end of 2015 where the first attack in the Ukraine was launched against three energy distributors who supplied around 200,000 people with energy, and therefore disrupting energy supply was the next goal, and they tested it in 2015, launched another attack in 2016, where at the first times energy distribution, energy supply was disrupted. And the suppliers, if you look at the energy suppliers, They have at the other side some needs to interconnect with Office IT because the managers want to see how much energy is supplied, how many kilowatt per hour are supplied, how many cubic meters of water are supplied. And there are remote connections now everywhere where these attackers in the Ukraine set on where they said, okay, we attack the Office IT and then we search one of the remote connections and get to these SCADA networks. We have system maintainers and they are often external companies. We have emergency services like support employees of the suppliers, and they have remote access via internet if you and sometimes there is a lack of network monitoring. So we have seen never syslog service in the last years. We have never seen SNMP monitoring in the last year in these networks. And they're in a real bad state. And if you look at one of these example networks, there are so much points where you can monitor in a network. So network intrusion detection is a key technology to to monitor these networks. You have a firewall and there is a SCADA network and there's a DM set for remote connections, and from the SCADA network there is a connection to a geographical wide area, to the rural area and to the metropolitan area where the single transformator stations are sited, where the substations are sited. And from the SCADA network, these substations, these transformation stations are controlled. So there are everywhere connections between small networks where you can start network monitoring. And that was our approach, that we said, okay, network monitoring could be key if one attacker gets into one of these small networks at the transformation station, one attacker gets into the Office IT and tries to hop into the SCADA network. That's the point where we can monitor these incidents. And the solution we found is called KRITIS Defender. KRITIS is the German abbreviation for critical infrastructures. And we used SuriCata because we tested it at some of our customers, and SuriCata very well performed. So our idea was to build up a security appliance for these critical infrastructures, and our idea was to take this appliance, bring it out to our customers. They can use it in their SCADA networks, they can use it in their transformation substations, they can use it in their water stations and so on. But SuriCata is not only the single tool on this appliance, because intrusion detection needs an ecosystem. I think everyone knows here that single SuriCata installation doesn't help in detecting incidents. You need tools for analyzing the data SuriCata generates, and you need mechanisms for processing, for alarming of events, and for the analysis of events. You need mechanisms for maintenance of the system. So the system design we thought about was we take the SuriCata instance or instances to an operating level of the system, and we split it from the UI level where the user is accessing the SuriCata appliance, the KRITIS Defender appliance, and define some interfaces between these two levels. So we can split it. It has some positive effects if we split it, not only security effects, but if the user accesses the web UI and there's the operating system UI in the background, you can split it on separate systems if you want to. And we use the RedisDB as data pool. We use the YAML files which are accessible out of the web UI to access Suricata configuration, the readers DB to read out the events Suricata generated. And at the monitoring ports of the appliance, we plug in the networks of our customers. And there's some, if you say, hey, I have one appliance sited in the server room of a critical infrastructure operator, there's some other points you have to monitor, and we said, okay, there has to be sensors out in the network. So from the central station, from the central server room where the SCADA systems are sited, there's a way out to a metropolitan network, and from this network there are connections to the substations, and sometimes they're not only connected over standard fiber connections, they're also connected over internet connections, they're also connected over wireless connections. And with that, if these substations are sited so much outside, you don't have anyone sitting in this substation as a person, and we want to monitor the networks in these substations, so we have to place some sensors there, and we use simple IPCs and industrial PCs, which are placed in the stations, and not every substation is vital, so we place this sensor in some stations. Think about a substation only supplying 300 people with energy is not that vital. Then a transformation station which supplies 100,000 people with energy. So there's the point where a sensor has to be placed. And the use of the readers DB was real good design decision, since our sensor points report as a standard Suricata installation, report their detection, report their events to the KRITIS Defender appliance via readers. In the KRITIS Defender appliance, in the readers database, a new event was triggered, and the UI can see a new event. So this design approach was not only made because with that it's an easy approach. So you have to think about SCADA systems have investment cycles about 10 to 15 to 20 years. So these networks are designed 5 years ago, and you can think about they will run in this decision the next 20 years. So network specification is really fixed, communication paths are really fixed, so we can say, if we define rules in our sensors, if we define rules in our KRITIS Defender, we can define these rules like the specification of the network is, because it will not change in the next years, and every event which is outside of the specification is an anomaly, and every event which is outside of the rules, we can say that's an incident. So we often use negations in rules. So if a command is not from the SCADA servers, then that could be an attack. And there was some other benefits when we looked at critical infrastructures. So event processing, manual event processing at critical infrastructures. There's a standard process. If an operator sits at his desk and there's an event about an outage, he gets the event presented, he confirms the event, he analyzes the event, and then triggers some action, like he pulls the trigger in, or he sends a maintainer out to the station. And this standard process could be used for incident response because the operators are well known to this process. So if an event triggers at the security appliance, at the KRITIS Defender, the operator gets this event presented and he can say, okay, that's an event, that's a security event. I confirm I got this event, I analyze it, I trigger an action like calling our CSIRT, calling incident response teams, and then I confirm this event is now closed, and it's some sort of a ticket system you can think about. Then there was another benefit that asset management at our customers is a very well-known theme. And this task of asset management, of risk analysis, of analysis of potential threats is very well defined. So they know actually where they have risks and where the risks are really high. And so intrusion detection rolling out is really, really easy because you don't have to analyze networks in prior, because they have done it. They have done analyzing of the networks, and you get presented from the customers at this and this point. We have real high risks, and this should be monitored with intrusion detection. So we can define a rule set. We can define the detection mechanism very well and very tailored to each customer because they have done risk analysis process in prior. So SuriCata supports syslog, event logging, and if our customers have a syslog server, we log to the syslog server as well. But in SCADA networks, there's really often communications about potential free contacts. Only 2 wires with 1 contact, and there's a signal switching the contact on or off. And we use it for signalization if there is an event, if there is an alarm, because our customers are real well known to this technique of alarmization of events by potential free contacts. So the KRITIS Defender appliance got the possibility to trigger alarms, to trigger warnings, to trigger infos over these potential free contacts over an analog way of data communications, because our customers are actually using systems who process these events, and they can put these potential free contacts on one of their RTUs or one of their PLCs and report it to the main SCADA system. So we got an interconnection between KRITIS Defender and the SCADA system, but there's no TCP/IP interconnection. There's an interconnection about an analog 2 wires. So the security of the SCADA system and the KRITIS Defender isn't affected if one of each sides has a security flaw. And the main reason for intrusion detection we built by ourselves was that we haven't found any system who was really able to monitor automation telecontrol protocols. I have here an example of IEC 6875104. That's, I think it's a standard protocol for telecommunication. It's short, IEC 104. SuriCata already can protocol pass DNP3. It's another telecontrol protocol, but as I heard, DNP3 is mainly used in Northern America and other countries, but in Middle Europe, IEC 104 is the standard telecontrol protocol. Makes it complex things about the protocol short, only to give you a short view of the protocol. Each RTU remote terminal unit, the think of it as it's like a PLC at a substation, and they have an internal addressing called IOAs, and these IOAs are some addresses of one switch, of one circuit breaker, of one transformation switch. And if you have a control to send, the SCADA server generates an IEC-104 packet and sends it to the RTU. The RTU takes that packet, says, okay, that's for IOA 1, and IOA 1 is the circuit breaker 7, and I will send a switch off command to circuit breaker 7. It's a real easy protocol. If the RTU detects at one measurement value, says, okay, we're out of range of the water stand in one of our water pools, then there's a measurement value generated from the IOA where the measurement device is connected, and it's sent to the server. So the packets which are used in IEC 104 are real easy to understand. There's a start byte, and then there's the length, some control octets, and the ASTU, think of it as the payload of the protocol. And thanks to Cisco, there was already some rules which can be used to monitor IEC 104. And there's an example here for a single command which is sent over IEC 104, and Cisco only uses regular expressions, PCREs. And the content 68 says, okay, this is an IEC 104 package because it's the start byte of an IEC 104 package. And then comes the regular expression which says, okay, if there is this value 2D, 3A, then it's a single command. And a single command, a single command should only be sent from the server. IEC 104 has, by design, some security flaws. So IEC 104 has no measure for authentication or for encryption. And so everyone in a SCADA network can send this packet to one of the RTUs and trigger a circuit breaker to switch off. And the Industroyer malware, which was used in the Ukraine 2016, used this security flaw. The Industroyer malware was somehow automated and scanned the network for RTUs and enumerated the IOAs on the RTUs and said, okay, if this is an RTU and these are these IOAs, I send switch off commands to all of the RTUs and to all of the circuit breakers, and the grid is going black. So this security flaw should be monitored. If someone is in a SCADA network and sending commands and he is not the SCADA server, there's a clearly incident. So we can use this example rule generated by Cisco to monitor a SCADA network for commands which are unauthenticated send. And this is the exemplar of the Industroyer malware, of the config file of the Industroyer malware. I switch over it. But these plain rules from Cisco can only be used to detect some single commands, some double commands, some measurement values. There's no real intelligence in this standard rules. So we said, okay, if we want a more detailed view on IEC 104 communications, we have to adapt these rules. And our approach was to use the Lua support SuriCata has. And using the Lua support, we could process the packets, the IEC-104 communication completely and say, okay, we can prove 104 communication about network specification. Is this single command in use? Some SCADA systems only use single commands. They don't use the feature of double commands. So if the SCADA system don't use the double command feature and we've seen some double commands in a network, then we can trigger an alarm because that's not a normal packet, that's a packet outside the specification. And we can bring in some sanity checks for measurement values if you say, okay, there's a measurement value and it's in the range between 10 and 20 and the measurement value is out of the range, it's under 10 or it's greater than 20, we can prove the whole payload of the IEC-104 communications, and therefore we can completely monitor IEC-104 communication yet. We don't have implemented an IEC-104 protocol parser because we don't had a need at the recent point to implement an IEC-104 protocol parser, but I've heard here in the crowd that there is a company who is already at this point implementing an IEC-104 protocol parser. So, what have we seen while implementing this system, and what have we seen while bringing this system to our customers? The system is now at 10 to 15 customers, and we have around 2 to 3 months now on lifetime of these systems at our customer sites. Specifications of system designers and specification of network designers are specifications, but the guy who implemented the specification had often another opinion of implementation, so the specifications in SCADA systems are often wrong or differs from original specifications. If we monitor SCADA networks with SuriCata, that works very, very well because the data throughput on SCADA networks we've seen is incredibly small, and the small data amount allows us to store PCAP files at 2 terabyte disk about for 6 months, 8 months in the history, so we can store real long time PCAPs with a real small amount of storage. And we don't have any performance issues. We used a standard network appliance, a standard firewall appliance, and installed an Ubuntu, installed a SuriCata, and there was, until the recent point, no performance issue because data throughput is so small in these networks. We have sometimes data throughputs in under 1 megabyte per second, and this on 1 megabit per second and below, and sometimes there's communication each minute, and IEC-104 communication is relatively small packet, so data throughput isn't an issue. We have something of work to do in the future because we've seen, okay, our UI hasn't depth filter options, hadn't depth analysis options we wish, so we will integrate the ELK stack in the UI in the next few months, and I think we will integrate some more SCADA ICS protocols if needed by rules and Lua support, or maybe by implementing a parser. I don't know what our customers want on protocols in the next years. There are some changes. There's an IEC 68150 protocol which will be used by some customer in the next 5 years. So maybe we will implement another protocol, maybe then as a protocol parser for SuriCata. So if you have any questions, I will be happy to hear them.
Can you tell us anything about your hit rate with the signatures through written? Have you detected anything out of the normal?
I don't understand it.
The signatures are written for ISE 104. Have you detected any uncommon or unwanted behavior in the SCADA networks?
We had detected some uncommon communications with IEC 104 signatures. So sometimes the system implementers and the system suppliers of the SCADA systems haven't implemented the IEC 104 standard by 100%. So they often differ from the standard. We have implemented the rules like the standard, and so the rules trigger often alarms at if we implement KRITIS Defender at a new customer site who has another supplier. So we have 3 to 4 branches meanwhile for different suppliers, which has different implementations of the IEC 104 standard.
Thank you.
How do I get the PCAPs out of the KRITIS Defender?
The PCAPs out of the KRITIS Defender, there's in the UI there's a download button, and we split the PCAPs by storage in 100 megabyte chunks, and you can, if there is an event, you can click on download, and the event has a timestamp. The 100 megabyte chunks have a timestamp, and the correct 100 megabyte chunk is searched on the disk and downloaded.
Is it also possible to get the full PCAP?
It's possible for our support employees, for the ASECO support employees, which have maintenance connections to the KRITIS Defender appliance. They can get the whole PCAP out of the appliance.
Is the maintenance connection a remote connection?
It's a remote connection, but it's recently a reverse SSH connection, so our customer don't have to punch a hole in his firewall, and he can switch on the reverse SSH connection if he wants, and if he wants to disable remote connection, he can disable the SSH connection. So that was an idea we thought about. If we make remote connections and maintenance connections, we don't force our customers to punch another hole in their firewall and to punch another hole in their security system.
Okay, thanks.
Am I right in understanding that the appliance is kind of the controller, and then you have these sensors, which are the SuriCata instances at the different locations that you're trying to monitor?
Yes, that's right. We have SuriCata, sensor instances using SuriCata, but the main appliance, the KRITIS Defender appliance, can also run on SuriCata appliance. So often if you place one of the appliances in a server rack, you will say, I don't want to deploy another sensor in the server rack, so all should be in one appliance. Differs from time to time and customer network to customer network, so it's
Right.
tailored to the customer networks.
That makes sense. Could you discuss sensor placement location in the context of the Purdue model? Because it seems like it's simple to say, oh, let's just stick a sensor here, but in reality, it's a little bit more complicated when you get into those ICS system setups.
Sorry.
Like where does the sensor go in the context of the Purdue model?
Where the sensors and so in this model.
Yeah, it's just, you know, in your ICS networks, you've got your different layers, and you've got your ICS sensors, and then you've got a, you know, a historian somewhere and things like that. And it's always sometimes a challenge to plug in a TCP/IP sensor in there. And I was just trying to figure out, you know, exactly a little more detail on these endpoints. You've got an RTU and a sensor point and I guess a switch or router. But
in this example, it differs from network to network. In this example, it's anonymous real example. So this customer had an RSTP, TCP IP ring around his geographical area he is supplying, and there was a substation, and each substation had a switch plugged into the RSTP ring, and we plugged in our sensor points into the switch because there's a TCP IP connection, and by TCP IP the RTU is connected. So if we monitor IC 104, it's a TCP IP protocol, so we can plug into the switch where the RTU is placed.
okay, and you're just getting a span off the switch from here. Thank you.
All right, any final questions? Okay, great. Thank you, Benjamin.